What? Test is next time. Yep. Okay, guys, here we go. What we are going to do today is we are going to solve 3 equilibrium problems. Now, guys, just refreshing our memory, you don't need to write this down. Here's what we know. We know that Kc is products divided by reactants. It's not quite that simple. Remember, the coefficients become exponents. But guys, we've got this relationship. And last year in general chemistry, you solved these. And it went one of 2 ways. We either gave you all the concentrations and you solved for K, or we gave you K and all but one of the concentrations and you solved for the missing concentration. Well, guys, you're still going to be doing that, but it gets better. And so we are going to learn to solve this equation initially in straightforward ways like we did last year. And then this is going to get a little nutty, but I really think you guys are going to appreciate the logic. So guys, again, that's all we're doing today, is we are solving equilibrium expressions in all their different forms. So guys, don't write this down, but this is sort of the overview of the day. What you're going to find out, guys, is that there are fundamentally 2 different types of equilibrium problems you're going to be solving. The one that you've already done, the ones that we did last year, were the ones where you know the equilibrium conditions. Here are the concentrations, solve for Kc. Well, guys, this is the thing that's going to make today exciting. You are going to learn today to solve equilibrium expressions when you don't know the equilibrium conditions. So now you're going, wait, how can I solve a ratio of equilibrium product and reactant concentrations if I don't know the equilibrium product and reactant concentrations? And the answer is you figure out a sneaky way to predict what they will become. You're going to love it. So guys, let's look at these one at a time. So this one first. You got 4 minutes to solve this. Pretend that you're taking the test Thursday. For the Haber process, Kp is this. In an equilibrium mixture of these gases at 500 Celsius, here's your partial pressures for H2 and N2. Figure out what the partial pressure of NH3 would be. It may be time to go wash this bottle. So guys, as you're muddling through this, thinking about pride, I am going to ask you all to leave. Because I'm going to have a ton of general chem kids come in. But I'm just going to let you know if you've got grades you should be careful of, which means I need to stop recording. But please don't go and then interrupt other teachers' pride time and say, Mr. Knappenberger, let me go. Don't throw me under that bus. So, guys, as you're working, I'm going to work too. Okay. Oh, can't start there. Oh, this isn't concentrations. Oh, thank you. Wow. 0.4. No, that's X. Good heavens. Did you guys get a number? Can you save me from my calculator? No? 0036? All right. Did I set it up properly? So that times 0.432 times 1.45 times 10 to the negative fifth, and then take the square root. I get 0.00224. And then, guys, understand this needs units, right? Yeah, ATMs. Talmadge, did you find your math there? Okay. Hey, guys, so let's talk about a couple things before we move past this. First of all, units. You'll notice that the units in this particular question works out to atmospheres because we're solving for a partial pressure. But guys, please make sure you're clear on this. What if instead they gave us the pressure of this and we were solving for Kp? What are the units for K values? They are dimensionless numbers. Guys, understand that the molarities or the pressures or whatever the units that are over there, even if they don't technically cancel by exponential values, they're understood to be a ratio that does not have dimension. So K values are dimensionless numbers. They do not have units. But that doesn't mean they don't have meaning. Guys, what does this tell you? Looking at the Haber process, what does it tell you that the K value is 1.45 times 10 to the negative fifth? That the equilibrium lies strongly to which side? The left. Guys, think about that. That is important. So guys, let's think. This is products divided by reactants. Whether it's concentrations or pressures doesn't matter. So our K value is smaller than 1. So which one of these is bigger, the numerator or the denominator? The denominator. This equilibrium strongly favors reactants, or you could say that it lies to the left. So guys, this equilibrium is strongly to reactant side. That's what Haber did. Haber figured out how to retweak this equilibrium so that the reaction favors products, which made him a lot of money. But you guys all okay with this? The math, the concepts, you're all good? Yeah. Did you put it in brackets, or you just wrote NH3?
I wrote it in parentheses. I had it right for
Yeah, frankly, on that one, Rebecca, I wouldn't chance it. I doubt if they'd mark it wrong, but I would just, yeah, I would be careful. Oh, and actually, as I'm saying that, I realized I should have put atmospheres on that one too. They are really particular about labeling your numbers in your setups. You know what I'm saying? Okay. So, guys, you good on that? You're good? Okay. So, guys, let's then talk about this. So, these numbers that we plugged in down here in the denominator of this setup, they're pressures, right? But they are pressures at what condition? Equilibrium. Yeah, 500 Celsius. But when the reaction reaches equilibrium. So guys, these are the partial pressures at equilibrium. Now this is going to get interesting, because we're going to figure out how to solve these equations when they don't tell us the equilibrium values. Could be pressure, could be concentration, doesn't matter. Guys, you are going to learn now to solve these. Notice what it says right here. Solve these when the equilibrium conditions are not known. So guys, how do you do that? Well, you may want to write down the steps. Do you guys realize that this is the first time all year you've been given steps? Have you noticed that about last year? Last year in general chemistry, there were always steps. Step for solving mass problems, steps for figuring out percent yield, steps for calculating empirical formulas. There's always steps. And you learned the steps, and then on the test, you just did the steps, right? All the steps went away. Now everything's different. Well, guys, I got steps. So ready? When you're solving these problems, first thing you got to do is write a balanced equation. That seems obvious. And then, guys, once you've got the balanced equation written, what you're going to do is you are going to create what is called an ice box. ICE is obviously an acronym. Now, guys, the power of this is in the ice box, because the ice box allows you to do some interesting predictive work. So what you're going to do is you are going to use X to represent the change in concentration that takes place between initial conditions and equilibrium. And once you've got that done, you use these variables to then create expressions that represent equilibrium conditions. Then from there, you plug these into the Kc expression and you solve for X. Then you work backwards and figure out the equilibrium concentrations by plugging X back into the table. Obviously, this means nothing to you, but having at least written it down, you can at least sort of reflect back on this as we do this. And guys, we're going to solve two of these. The first one is sort of gentle and the logic is wonderful. Second one's a little nutty. No less wonderful, just nutty. But by the way, guys, this icebox stuff, you are going to be solving icebox expressions almost every day for the rest of the year. Hi there. How are you? Thank you. Do you want me to get the door for you?
Yeah.
Here, let me reach around back. There you go.
Thanks.
You're welcome.
Good. Talkative.
Oh,
Thank you.
I do my best. Thank you, guys. Have a good day. All right. So, guys, you ready to try this out? You good? You're still writing. You're writing. Why don't you just print the notes? Goodness gracious. What? No, actually, it's interesting. It doesn't. There's actually really, we haven't talked about this. There's tremendous research out of the Harvard School of Education showing that note-taking actually decreases your learning. Yeah, you're distracted. You're not learning. So, you ready for this in order? How does note-taking relate to learning? Well, if you take notes, your learning will go down compared to somebody that's not taking notes and just listening. So then that would seem to indicate don't take notes. Well, guys, it turns out that that's not true. The question is what you do with your notes. So if you take notes and just put them away, which is what you guys do, you're decreasing your learning. If you take notes and review them within 6 hours of having taken them, then your learning actually goes up. So it's not the note taking, it's what you do with the notes that's really important. But guys, it turns out there's an even better way to learn. I can show you the research if you want to see this. Guys, they proved that the best way to do this is take notes into the notes. So pre-print the notes. So students that were given the notes and then were simply annotating and taking notes into the printed slides as they were learning performed better than even the students that took notes and then read them within 6 hours.
Except there's times where I can remember.
No, I mean, I understand that there's always personal differences, but the research is bearing out that the best way to learn is to take notes into the notes. So understand you haven't been trained that way, and you've got to get over the initial nervous reaction of not writing everything down. But but research shows it's the best way to learn. Okay, you guys ready to do this? Here we go. 2 problems. That's all we got left today. Number 1 says this. So guys, the question is this. You have a mixture of 5 times 10 to the negative third moles of H2. 1, and guys, don't try to write this down. We're just going to solve this together. You can look at the slides later if you need the question. You've got a mixture of 5 times 10 to the negative third moles of H2, 1 times 10 to the negative second moles of I2. Put it in a container, a 5-liter container at this temperature. Let it come to equilibrium. You analyze the final mixture. You see that in the equilibrium mixture, the HI has a molarity of this. Calculate Kc for the reaction. Things just got real. You ready? Guys, this is the way to do this. This is why I gave you steps. Go back to the steps. What's step 1? Write a balanced equation. But guys, just trust me on this. Don't do it until you see me do it. We're going to go red. Guys, when you write your balanced equations, you need to make them big. So the balanced equation goes like this. We've got H2, and we've got I2, and this is in equilibrium with our product, which is HI. Make them big. Spread them out. You'll find that you may even want to make these as wide as your paper. Now we need to balance it. It's really just that, right? All right. So now, guys, we need to teach you the new stuff. So, the idea is this. We are solving for KC. In order to solve for KC, what do we need to know? Concentrations at what conditions? Equilibrium conditions. But guys, you will notice that when they analyze the equilibrium mixture, the only thing they give us is the molarity of HI. But that's all we need. And here's why. Guys, what we are going to do is we are going to leverage what is called an icebox. So down the left-hand side of this balanced equation, skipping a line for each one, write the letters ICE. Now these are obviously an acronym. And guys, the acronym stands for initial, change, and equilibrium. Now guys, please do not do this, but let me explain to you what you're now looking at. You are now looking at a 3 by 3 grid. Don't write that down. But you are now looking at a 3 by 3 grid. And guys, remember what eventually we're trying to do. We are trying to solve for KC. But in order to solve for KC, what do we need to know? Concentrations at equilibrium. That would be these. So guys, in order for us to find KC, we need the values that go in the circles. So let me clean up my mess. Oh, poop. I'm going to have to do this the old-fashioned way. Okay. And oh. Why do you guys always laugh when things go wrong? Here's what you need to do. When you decide to get into business and you start making presentations to clients, when that goes wrong, call me and apologize. No, I do. No, I am convinced that teachers are the best salesmen on earth because I'm tricking a bunch of 16-year-olds into caring about chemistry. Business salesmen have got it made because the people that they gather together in the room have already demonstrated a desire to buy the product. You just have to convince them to buy it from you. I've got to trick 16-year-olds into caring about this crap.
Maybe in a general kind of class.
Oh, no. Oh, no. No. If you believe that that's the case, then you've only had good AP teachers. Okay, so guys, here we go. We are now going to fill in the boxes. We are now going to fill in the boxes with all the information that we've got. Now, guys, here's the first thing you got to understand. What kind of information goes in the boxes? Concentrations. So let's now go back to the question and let's glean and organize all the information that we can find. So guys, here's a bit of information that we're given. 5 times 10 to the negative third moles of H2. But you'll notice that this and that are placed in the container and then allowed to come to equilibrium. So this is not an equilibrium amount. This is an initial amount. So this is going to go on the initial line. But guys, right here, I cannot write 5.00 times 10 to the negative third moles. Why not? It's not a molarity. So what I would do, what you're about to do in your notes is this. Do it with me. Down beneath here, I'm going to do it on a separate page. You're going to go molarity is equal to moles divided by liters. Moles is 5.00 times 10 to the negative third. Volume is 5.000 liters, and that's 1 times 10 to the negative third molar, getting very sloppy with significant digits. But guys, I'm going to make it even worse. 0.001 molar. I'm going to just write it out as a decimal. Do you understand what we just did? Okay. Now, guys, while we're here, let's do the same thing with this. Our other number of moles is 1.000 times 10 to the negative second divided by 5 liters. This is 0.002. And guys, understand, I'm not giving you permission to get sloppy with significant digits. But this is not me trying to teach you significant digits. This is me trying to teach you how to solve ice boxes. And so I gave you legitimate data, but I am going to just write these down to one significant digit so we don't get caught up in the numbers. We can figure out the process. Are you good? Okay, so now taking these numbers and moving this back, here's what we now know. We start with 0.001 molar H2. And we start with 0.002 molar I2. And guys, from that, we now know everything that we need to know in order to fill out the bottom line of this thing. Check this out. Guys, the first step involves some logic. When a reaction starts, how much product do you have? None. Now, guys, watch this. We are given one more bit of information. It tells us analysis of the equilibrium mixture shows the concentration of HI to be this, 0.00187 molar. Where does that fit into our icebox? Bottom right. That is an equilibrium concentration of HI. So I'm going to write that, trying to get this sort of lined up, 0.00187 molar. And guys, guess what? We now know everything that we need to know in order to figure this out. Do you see how the dominoes fall backwards? By knowing this, what do we now know? The change. This starts at 0 and goes up to this. So this change is plus 0.00187 molar. Now, guys, check this out. If this went up by 0.00187 molar, what happened to these two? They both went down by how much? Half of that. This is a 1:1:2 ratio. So guys, think about it this way. If this went up by 10 molar, each of these went down by 5, because this is happening at twice the magnitude of these. So if we take this amount and divide it in half, it'll give us those amounts. So taking 0.00187 molar and dividing it by 2, this went down by 0.00094, and this went down by 0.00094 molar. Now we can do the subtraction. 0.001 minus 0.00094 is, and again, guys, sloppy with significant digits, 0.00006 molar. and 0.00106 molar. Now do you see what we do? Plug them into KC. Go ahead. These two, subtracting. 0.001 minus 0.00094 is this. 0.002 minus that is this. So then, guys, to solve for KC, we go KC is equal to products. That's HI squared divided by reactants. That's H2 and I2. And then moving over, our H2 is our HI is 0.00187 molar squared divided by 0.00006 molar times 0.00106 molar, and doing that math, 0.00187, square that, divide that by 0.123406, divide that by 0.00106, and guys, I get 54 significant digits are kind of out the window at this point, but I got 54.98. Can anybody confirm that number?
Yeah.
Am I okay? Okay. So guys, what did we learn? What we learned is we can solve equilibrium expressions when we're not given equilibrium conditions. We do that by setting up this initial change equilibrium icebox and using that predictively, given the little bit of information that we are given, to figure out or infer what is happening at equilibrium given what we know about where we started and how it changed. We can then take that information, deduce what our equilibrium conditions are, and then use that to solve for KC. One of the tricky things is look out for the stoichiometric relationships. It was 1 to 1 to 2, and we have to respect that when we're talking about our change factors. You good? Because this gets crazier. This was the pretty one. You ready for the crazy one? Guys, what could make this crazy? Well, the answer is, what if they didn't give you this? Guys, this was the linchpin. This was the capstone. This was the thing that made everything else possible, because based upon this change, we could come up with, well, actually, it's sort of based on this. Based upon this, we could infer the change, which gave us that, which brought that down, and all the pieces fell together. But what if they don't give us that? Then we start using variables. This is making Mark nervous. 1 liter flask, 1 mole of hydrogen, 2 moles of iodine. What's it do? Oh, hold on. Yeah. There we go. So guys, same reaction as before. Why is KC not 54 point whatever we figured out? Temperature changed. But we're going to solve this. It says now we've got a 1 instead of a 5 liter flask. You got a mole of H2, a mole of I2. KC is this. What's it do at equilibrium? Shall we? Here we go. So guys, first thing we need is a balanced equation. We've already written it. H2 plus I2 in equilibrium with 2HI. Then we're going to icebox this. I, C, E. And now, guys, let's start plugging stuff in. Did you notice I made the numbers a little more easy to work with? So, guys, what do we know? So we've got the number of moles of H2. We know that we can't plug that in because it's not a molarity, but isn't it nice that it's a 1 liter flask? Molarity is moles divided by liters. If it's 1 liter, the moles and the molarity are the same. You should show that as an external calculation, but we don't need to. So guys, where does that fit? Where does the molarity of H2 fit? It is the initial molarity of H2. And again, guys, I'm going to take liberty with significant digits, 1 molar. Do y'all understand where that came from? Molarity is moles divided by liters. 1 mole, 1 liter, 1 molarity. Okay, now guys, we're also given 2 moles of I2. Where does that go? The initial molarity of I2, again, dividing by the volume in an external calculation, we see that that's 2 molar. We're done. That's all they gave us. Guys, that is all of the pertinent information that they gave us in the statement. So now let's talk about our goal. Please don't write this down. But guys, let's talk about our goal. It says, what are the concentrations of H2, I2, and HI at equilibrium? So guys, where will those be in the icebox? What are we solving for? What's our goal here? The bottom line. Literally, what's the bottom line? We want to know the concentrations down here. Because how are we going to do that? Well, don't write this. Well, no, we can write this down right now. Let's just do it. So guys, in order to figure that out, here's what we're going to do. We're going to go KC. You can just do this with me. So guys, here's the trick. They gave us KC. We are trying to solve for those variables, well, these factors. We're trying to figure out this and this and this, which is the bottom line of the icebox. How are we going to do that? Well, guys, this is how this falls together. This is pretty slick. You ready? What else do we know about initial conditions? 0 product. This is a 0. Now, from there, guys, we can talk about one really brilliant piece of logic. It's simple, but it's brilliant. What happens to reactants during reactions? They go down. What happens to products during reactions? They go up. How much? We don't know. So let's call this X. Let's say this goes down by X. If that goes down by X, if H2 goes down by X, how much will I2 go down by? Also X. And how much will HI go up by? 2X. Good. Plus 2X. Guys, do the ratios and the signs make sense? Reactants always down, products always up. It's a 1:1 to 2 ratio. So now, guys, what will our mixture look like at equilibrium? 1 minus X, 2 minus X, and 2X. Now we can plug these in. Here's what we know. We know that 51 is equal to 2X, the quantity squared, divided by 1 minus X times 2 minus X. Got it? What? You okay? You guys okay? Am I good? Okay, now guys, I'm going to rewrite this because I need more space. So 51 is equal to 2X 51 is equal to 1 minus x. Okay, guys, I'm glad you caught this, but understand, a lot of you are going to write this down. If you don't understand the context, this is the mistake that tends to trip people up. You forget these parentheses. You simply say this squared, and you write down 2x squared. Understand, it's the entire 2x that's squared, so it's 2x, the quantity squared. So what I wrote down over here is wrong. It's not that, it's this. Does that make sense? Now how do we solve this for x? Well, we've got 51 is equal to 4x squared divided by 2 minus 3x plus x squared. I understand they no longer call that the FOIL method. First, outside, inside, last. Do they still call it that? Foiling? Okay. So are you guys all okay with how we got that? Multiply the first factors together. 1 times 2 is 2. Then your inside factors, this is minus 2x. This is minus 1x, negative 2x, and negative 1x is negative 3x. And then x times x is x squared. Okay, then guys, we need to bring this over to solve for x. So we're going to have 51 times 2 minus 3x plus x squared is equal to 4x squared. Then we distribute 102 minus 153x plus 51x squared is equal to 4x squared. Then we bring the 4x over and put this in standard form, and we end up with 47, oh, that should be squared, 47x squared minus 153x plus 102 is equal to 0. Now, guys, grab your TI calculators. You can plug this, and I don't know how, but I know that some of you do. Guys, you can plug this into your TI calculator, and it will resolve it for you. If you don't know how to do that, and I'm not going to spend the time to do it, you can use negative b plus or minus b squared minus 4ac all over 2a. That's the quadratic formula. And you can plug this into that, and you can solve it longhand. I would encourage you to figure out how to do it automatically on your calculator. But guys, if you don't understand the way this goes, guys, you'd better understand this. Hold on, Joe, just a second. And you're welcome to help, but guys, hear this. If you do not understand that whether you do this in your calculator or whether you do this with the quadratic formula, it results in 2 answers, and you need to write them both. Does anyone not understand that? Okay, then go ahead and do whatever you needed to do. Guys, I need to know the answers, though. Joel, I'm sorry, I didn't mean to interrupt you. Were you okay? Okay. So give them to me. 2.3, 0.94. Okay, and again, we're being really sloppy with significant digits. But guys, get to the point where you get these answers. We've got time to wait if you need. What?
It's pretty easy. You just go to apps, you press 9, and then
Would that be universal to all calculators? Okay. We're not done. Yeah, guys, we're not done. I want to wait for, this isn't even close to the answer. I just want to wait for you to figure this, get the math figured out. So Joel, what does it look like when you bring up the window? Could you do it from scratch?
I just have an app that allows me to solve polynomials for roots up to 10 degrees, but it comes preloaded on these calculators.
Oh, cool. And so once you fire up that app, it's just asking for input, and you just plug in 47, negative 153, and 102.
And then ask your calculator for where the zeros are on the graph.
Oh, that's true too. Interesting.
I'm not sure what it is.
What? That's what you have to do? Okay. So, but did it work? You're okay? So guys, let's do this. If you're still needing some Zen-like calculator guidance, let's give you another second, but it seems like most of us are being successful and we're nowhere near done. So give you another 30 seconds and then we're going to get together. Okay, guys, I'm going to pull us together. We only have 3 minutes left, and we've got to see this through to completion. So I know that some of you are frustrated. Some of you are intrigued. You're trying to figure out your calculators. I need you to make a conscious decision right now to put that out of your mind. Trust that these answers are correct. So, Anna, I'm just going to ask you to put the calculator down. I know this is unfair to you, but it would be more unfair to not see this through to the end. I know that eventually you're going to figure out your calculators and come up with 2.3 and 0.94. You need to know what to do with those numbers. You can figure out the other without me. You can't figure out this. So guys, here's the deal. When you learn to figure out the quadratic formula in math, your math teachers told you both of these values satisfy the equation. If you plug 2.3 in for x, solve it, you're going to get 0. You plug 0.94 in for x, solve it, you're also going to get 0. And that's really neat in the sterile environment of math. The problem is that in chemistry it doesn't work that way. Because guys, chemical reactions cannot reach two different equilibria. And remember what these numbers are. These are the x's in our ice box. And the x's in our ice box are part of the equilibrium concentrations, right? But reactions don't get to pick which value of x they use at equilibrium. So let's put this in context. So guys, our values are what? 0.94 and 2.3. Guys, one of those doesn't make sense. Which one? 2.3. Because guys, if you subtract 2.3 from 1, what do you get? A negative number. If you subtract 2.3 from 2, you get a negative number. Guys, that makes this value nonsensical, and therefore you can throw it out. So the value that satisfies the ice box is the 0.94. So then what you do is you come through here and you go 1 minus 0.94, 2 minus 0.94, and 2 times 0.94. So this is 0.06 molar, this is 1.06 molar, and this is 1.884 molar. Guys, understand you wouldn't do that math in the ice box. You would actually carry it on. What it should look like is this. You would go concentration of H2 is equal to 1 minus X is equal to 1 minus 0.94 is equal to 0.06 molar. Was that H2? Did I do that right? So concentration of I2 is equal to 2 minus X is equal to 2 minus 0.94 is equal to 1.06 molar. And then concentration of HI is equal to 2 times X is equal to 2 times point, good heavens, 94 is equal to 1.88 molar. That's what the calculation looks like. You don't have to explain why you're throwing out the nonsensical solution, but guys, if you get two values that work, you did it wrong. You did the math wrong. You can't get two possible answers because the real world won't allow two different sets of equilibrium conditions. So that should be a warning sign to you that you did something wrong. You get the idea? So, does this mean that we're going to be doing the quadratic formula for the rest of the year? No. You're going to find out in chapter 16, actually chapter 17, there's a sneaky little thing that we can do to simplify these ice boxes and get rid of the quadratic formula. It's a beautiful thing, but I'll show you next time. So guys, test on Thursday. As Jake and I were saying, you will have 2 free response questions on the test. One of them will be rate, one of them will be equilibrium stuff, and then of course multiple choice. We'll see you Thursday. Here's your homework. Right there.